Yes, sir.
Okay, thank you, madam. So thank you all for joining this wonderful program, and thanks Gayatri madam. So she followed up like anything. So today morning also she called so many times the conversation, and finally the day has come. And also thanks all the organizers and the participants and the institution as well for the wonderful program. So today I'm going to touch upon the just an introduction to the 5G technologies in various perspective. One is from the, for example, technology perspective. The other one is use case perspective. Use case means application perspective. What are all the key enablers we have in the 5G, and some of the simulation system level things, and also then we will have a standards perspective. So what we have in the standards and other stuff. Okay, because I'm more into these areas, that's why I would like to touch upon those areas. And if we could see that in this so why I put these anime like GIF files is that, so these are all kind of a driving force for the 5G basically. So the first one is like we were facing some kind of issues, like when you have this kind of coverage, cell type of coverage, we are facing the issue of, for example, interference. Okay, interference is coming over here in this vicinity of this coverage area, cell coverage, cell type coverage. For example, traditional 2G, 3G, and LTE networks, we have three antennas covering 360-degree almost. Okay, so in this, that's why we are going for an 5G. We are going for a beamforming technique as well, wherever we are having these kind of issues. Okay, this is one part. The second part is like we can see that this is a single user MIMO and a multi-user MIMO. Okay, this we have in the 5G in order to for example, you can see that in this area, whether you irrespective of user is there or not, we are keep transmitting powers. Whereas here we are only pointing the beams, or pointing the power, or utilizing the power to communicate with the user wherever he is, or he or she is. Okay, and here is, you can see that this is how, for example, if you are having beamforming kind of thing, this is how handover happens when you have a beamforming kind of a scenario. Okay, it's not a traditional one, it's a kind of a beamforming scenario, how the mobile will get handover to the one cell, from one cell to the other. The here, this is the MIMO. Basically, the requirement for the MIMO. Why we require MIMO? Because we need to have, for example, spatial multiplexing, and also we have to make use of the multipath to communicate the who is in the. For example, you can see here there is a building. Some car is going behind this building and getting disconnected over here. But when you apply the MIMO, for example, 8-layer or 4-layer MIMO, and which will make use of this multipaths, so that I can able to communicate by just to have a reflection from here, and then I can able to communicate the user who is behind this building basically. So these are all the some of the technologies we have in the 5G, that is driving 5G basically. And this is my agenda basically. Okay, yeah, we can see that we will start with the introduction. Okay, in that we will see so many features, enablers, and use cases, and fundamental theorem, like why we always tell that the 5G has a enormous capacity. How come? How enormous throughput? How come it is it is derived from fundamental Shannon's capacity theorem? Then we'll see fundamental this like traditional MIMO system, and also the massive MIMO, and phased array beamforming, which is driving the massive MIMO basically, and that we will see, and some of the simulation testing, how it is done, and those kind of we will will likely touch upon. Then at last we will cover the standards perspective, which is very important to know. Okay, because which is openly available, and then anybody can access and then see what is going on in the standard as well. Okay, now I'll start with the introduction of 5G. Like we can see that 5G is just not, for example, every we call it as a generation, right? First generation, second generation, third generation, fourth generation, and fifth generation. We are now into fifth generation, and already research has been started for the 6G as well. Okay, so here you can see that in 1G we were having analog technology, where we will have only voice, not the text messages. But in 2G we had kind of some kind of digital modulation schemes came up, and then we had some kind of mobility we had, and also roaming, and some of the minor slow, and we can say data, like data, SMS came into picture, GPRS came into picture, and Edge also came into picture. When you move on to 3G, there is a some kind of shift has happened from in terms of the calls. Like in 3G we had a video call as well, and some of the multimedia message you can see, MMS you can send, those kind of stuff came into picture, and also some increase in the data rate. But then from 3G to 4G, yeah, kind of a paradigm shift in the voice quality, and also VoLT came into picture, where IP based networks came into picture. So till 3G, it was some part of the network was connected with the analog, for example, circuit switching based networks there. But in for LTE, predominantly they were using fibers as well as the IP based systems basically. So which has driven the speed, high speed, as well as the voice quality, and also handover also pretty much great. And because we are making use of WCTM as well, and also the speed that it supports. For example, when you are traveling in vehicle, when you have a 2G, it will have a kind of some kind of glitter in your voice or anything. But here it is not like that. So it is much better than that what we had in 2G time era. Now 5G, it's a great paradigm shift, because whatever you call, for example, IoT, machines, private 5G, enterprise automations, and medical telemedicine. So all are coming to picture in 5G. A paradigm shift, because it is going to work with collectively with the several allied technologies as well. For example, Sigfox, LoRa, and so many Wi-Fi technologies as well. Because here the 5G, where for example, IEEE based technologies, also IEEE technology like 802.11 series of technologies going to work with 5G in coordination with 5G. And you have, for example, 3GPP based IMT, whatever standard you call, everyone is coming together, and they are interoperable, and then started working on that. In 4G itself, we might have witnessed that Wi-Fi based call, right? So when you have Wi-Fi network, the call will be routed through Wi-Fi network only. You might have seen that. So that is already in the 4G LTE advanced, but in 5G it is predominantly going to be there. Okay, in order to offload some of the network capacity, network workload to the allied network, so that for example, when you are getting into the buildings, right? So where you cannot give coverage perfectly to the user, right? That point of time, you can make use of this Wi-Fi and then give coverage to the user, so that better user experience can be uptime. Okay, and you can see that you see this is how the 5G started. Like it started from LTE advanced itself. Okay, and then they added some IoT things, IoT applications, and then we used then they having unlicensed spectrum they were exploring, and for the 5G especially, and also predominantly small cells. Okay, integration of small cells and the ultra densification, we used to say. So in 4G era, if you have 10 sites, means here you will have 15 sites or 20 sites basically. Then exploring millimeter waves and network functional virtualization. So network function virtualization is the one driving the latency issues, and also the use case based approach, network approach. We'll see the later network slicing approach. Then we'll have a new radio technology, which is 5G basically. That's why in 5G, you might have seen NR radios, like that. You might have seen 5G radios, you might have seen NR radios, so which is new radio basically. Then if you use case perspective, you can see that three major objective of 5G. One is EMBB, enhanced mobile broadband, which uh, drives the higher bandwidth speed basically. Then you will have a low latency, ultra reliable low latency, and then machine type communications. Okay, so here so all are together. You can see that each has its own purpose. For example, in terms of latency, see this does not want any much latency issues, but it will has latency issues, and it need not have a much speed as well. But EMBB need high speed spectrum basically. So that's based on that only. You can see that the green one. So green one is what they are targeting is like a spectrum efficiency, user experience, data rates, and other stuff. On the E and F is they are targeting for the latency and mobility. Mobility is very important. Okay, these are the two things they are expecting over here. So that's how they arranged these use cases. Okay. Now in 5G, especially, you can see that these are the some of the pillars of 5G, like for example, high capacity per kilometer basically, and then high data rates greater than 10 Gbps, and reduced latency less than 1 millisecond. By the way, latency is nothing but we used to call it as TTI, transmit transmit time, total transmit time, which means when you are initiating a call, for example, okay, TTI means when you initiate a call, when you dial the numbers, okay, some number, okay, and the call is dialing, it will go to BSC, for example, base station, and then BSC or RAN, you can see. Then it will go to get it verified from the MSC or other support subsystem. Then user is authenticated, he is having balance to make a call. This verification will happen. Okay, so how much is the time it is taking from the from the by dialing the number and to delete get call is connected. Okay, so that is the time we call it as the TTI. Though that is why latencies should be very low for the, for example, in order to respond, the car is traveling at, for example, 500 kilometers per hour. So I have to respond in spontaneously. Otherwise, what happens is car may collide. In a fraction of seconds, car may collide, right? So that a point of time, that is driven in the various approaches we used. We will see later. Next is massive device connected devices and other stuff. Okay, and especially energy savings. That is what they are targeting. Okay, I will tell you later and how it is done, and the ultra reliability and other stuff. Okay, it's been covered. So energy saving, how they are doing. For example, you can see that this is the LTE cell coverage. Okay, LTE or 3G traditional coverage. You can see that. You see these devices are there. So it is covering only these devices. Whereas here there is no device, but still it is transmitting. So we are wasting our energy in this particular direction, basically. Okay. But so that's why we could not able to cover, cater these users, right? But in 5G, we are using beamforming based approach in some of the radios, not all the radios. Some of the radios are still like this only. Okay, for example, 44 radios will have a coverage like this only. Okay, but when you are going beyond 88R or 16T 16R or 32 32R, the TD means transmitter, R means receiver. Okay, and we'll have this kind of beams, so that way what is that visible advantage is that we are covering a larger range basically. Okay, larger range, and also reliability is enhanced because we are pointing the beams towards the user. Okay, the next thing is that we are avoiding the energy save, we are ensuring the energy savings over here. It is very clearly visible from this picture basically. Okay, now am I audible? Hello, hello.
Yes, sir.
Okay, okay,
Your audio.
okay. Thank you, because okay, okay. So key enablers, like one is very high speed data rate. How we are achieving, we should think like we see there are many factors are there. We will see in the Shannon's capacity theorem. Like many things. You can see that use of multiple input, multiple output, advanced modulation schemes. How we are going to make the spectral efficiency higher. For example, if you are using 100 megahertz, how we are going to use that 100 megahertz to transmit more the power, more the data, like beyond certain data rate. Okay, so here we can see that, you can see here in 2010 they started with the 70 mbps speed for the 5 LTE. Okay, downlink is 10 megahertz. They till for 3G it was 5 megahertz. Now they started with the 10 megahertz and a 64 CAM. So modulation schemes also very important. For example, if you use BPSK, you can only code only 1 bit per symbol. Okay, but whereas if you go for a QAM, I think 2 power 4 is 2 power 5, 2 power 6 is actually 6 bits you can go for code for the per symbol basically. So that way you have what advantage you are getting. So you are say per symbol you are mapping the number of bits as higher and higher, and when you go for higher modulation scheme, higher order modulation schemes basically. You can see that it is clearly visible. For example, when you have a 10 megahertz, 20 megahertz, what is the speed we are getting? And also 2 cross 2 MIMO. MIMO spatial multiplexing also playing a major role. You can see here that 64 palm, 300 Mbps with the carrier aggregation. Hello? Here is the carrier aggregation take into place. So you can see that 2 into 20 megahertz basically. Two carrier will be there with which will have this kind of capability, so that we are aggregating the speed of 300 Mbps. Similarly, it's going on, and then we can see that in 5G, you can see that 256 QAM. Now they were there. We are talking of 1032 QAM as well. Okay, and massive MIMO NR, and we are talking of 100 megahertz, more than 100 megahertz, 200 megahertz as well, along with the carrier aggregation. That's why we are getting the speed of 10 Gbps, more than 10 Gbps basically. Next is the heterogeneous devices communication, which is for example MMTC. Here the thing is heterogeneous means, for example, earlier in 2G, 3G era and all. So network only we talk with the network, other networks. That's all. Okay. Not it will not talk with the IoT devices or any Bluetooth devices or anyone, right? And Wi-Fi devices. But in LTE, they made use of Wi-Fi technology as well to offload some of the work to the some of the data speed to the data hungry application to the or use case to the Wi-Fi, right? So here also it's going to happen like that. So we are going to have, for example, machine type communication IoT devices. For example, smart agriculture, which will be updating the, for example, paddy cultivation and other stuff through 5G network. And environment, IMD, like a meteorological department, is going to closely work with, and will have real-time updates, right? So, for example, in your mobile, you might have seen, right? So now we are, capturing from satellite data. It is updating in your mobile. Wherever you go, it is updating automatically. That depends upon the position. It is updating that today you are going to have rain at this time, that point of time, that all that stuff. It is going to be enhanced. Okay, smart homes. Anyway, we are having, and autonomous vehicle transport logistics, especially industrial automation is going to be a industrial IoT is going to be a big role, because for example, some of the meters, right? Some of the, for example, thermal power plant and all, thermal power plant, or petroleum industry. So a human cannot go and take the reading in on and off. Okay, cannot go and detect the fault is indeed that. So that point of time, we can make use of this IoT devices to detect that, and then keep reporting to the backhaul basically, or we can say system. Okay, and smart buildings. So to optimize the AC, air conditioning things, and also the water usage and other stuff. So we can make the smart buildings, and many more applications are there. Okay, in the heterogeneous devices. And this is one thing. For example, you can see that IoT has a broad picture basically. So here we can see that there some of the applications will have a latency issues. Connected car, and aviation also going to be connected. For example, in-flight. So now you might have seen news from the Nokia that they are going to launch the LT in space as well. Okay, so that kind of stuff, in-flight experience they are going to have, and also consumer wearables. We might have seen. See, now we are all used to the gadgets, right? So when you are going in the cycle, riding the cycle, you can see that which travel, how many kilometers you have gone, which route you have followed. All that stuff is going to be coming, and then people are sharing in the WhatsApp and other stuff, right? So similar cellular devices and many more are there. Virtual reality, that you can be in the virtual world as well with the help of the virtual reality. The stadiums. So stadiums are the, you might have heard the news from the Japan Tokyo that Olympic. They are going to use multiple, because they are in stadium. No, more than 2 lakhs people are gathered there, and they stream the videos, they upload the videos, download the videos, many things will happen, right? So that time you have to cater for that kind of applications, where this IoT can play a big role there. Okay. Next is low latency. So how we are achieving low latency? So in network itself, we have, in 5G we'll have a network slicing. Slicing means, for example, see, if I am detecting the application, like for example EMBB, like high speed data, high data rate application. For example, I am going to download my some books, or movie or anything, right? It will follow some kind of architecture like this. Okay, and when you go for IoT slice, then see, in EMBB we don't bother about latency. We only bother about the speed. Whereas in IoT, there is yeah, slight latency issues there, or also we do not want any much speed as well. Okay, so that way it will follow the other kind of architecture basically. The third architecture is, like for example, You can see that ultra reliable low latency. For example, when it detects a V2X application device, then it will follow certain architecture in order to cater for this particular low latency basically. So you are seeing this kind of thing, right? So how it is possible? Because now we will be seeing one slide how it is possible, because everything is going to be in software now. Okay, everything is going to be software now. Okay, so for example, like you have MATLAB. Okay, you can generate the signal, analyze the signal, and then you can just give as an feed as an you make a package and then dump it in FPGA by converting the HDL program, and then you dump it in FPGA, and then you can start working. That's all. So most of the function, right, amplification, modulation, and everything. Earlier we used to have all hardware, right? Now we do not want all that stuff. So all can be done in the software itself. Okay. So most of the hardware functions are being converted into software. That way we are achieving this kind of slicing, because in software you can control any flow that you want, right? That's why it is going on. Next is use cases perspective. So one is major use cases, autonomous cars, everybody talk of, right? That technology is basically driven by two basically standard, like technology. Like one is DSRC, dedicated short range communication. The other one is CV2X. CV2X is cellular vehicle to everything. Okay, so here you will have for example, your vehicle will have onboard unit. Okay, or your device called onboard unit, or UEV used to say. So what will happen is, you will have, for example, yeah, roadside unit will be there, and also the cellular towers will be there. All will be communicating to this. Here you can see vehicle to network, vehicle to infrastructure. Vehicle to infrastructure means, in infrastructure, like the kilometer board. That board and itself will have a device, and then you can come. The car can communicate with that, and roadside unit will be there. So roadside unit means on the side of the road you will have some of the unit which will communicate with the cars and other stuff. So all the stuff is going. So here the coordination is happening between the network, between the infrastructure, between the roads, between the satellites and everything. All going to come together, and then going to support this cause, for example, because we cannot give any chance, right? So if your coverage is poor from this tower, it can pick up from the signal from this infrastructure. Okay, that way we are achieving this, because we are promising that more than 500 kilometers per hour you can drive with autonomous cars. So how come it is possible? Because of this kind of services only. And also cloud services also. Cloud, okay, because the cloud means we are running only the normal servers, right? So in that, software is running, right? So software can have a low latency, very low latency. It depends upon the algorithm, right? That way we are achieving this kind of catering this applications. Next is private 5G. So it is very nowadays, many companies are investing heavily on this, and we have EVR as a company. We also have some customers for this. Okay, private 5G is going to be a predominant one driving force for the 5G basically. So why? Because they want to automate the industry, right? So they want to, for example, preventive maintenance and other stuff. They want to do the automated automation basically. For that, they need these kind of things. Okay. Next is telemedicine. Telemedicine means, for example, you might have heard from the LinkedIn or YouTube or somewhere that remote surgery have been successfully completed for the banana, right, through from London to America. So the doctor was sitting in London, I think so. Okay, they were doing surgery. The banana was then in the America. Okay, so telemedicine that way, because here it is very low latency applications, right? For example, if you are doing a heart operation, if you miss some critical operation, if you miss 10 seconds also, which can kill the person, all right? That way it is going to be a low latency thing. And also other thing is that with the help of the IoT devices, for example, if your pacemaker is there, the pacemaker conditions can be reported to the doctor on and off, for example, monthly basis or something like that. So there you can use of IoT devices, right? And that's how it depends. Nowadays they are using that. So where is the the Javan is located, or where is the army personnel is located, where they are going, which direction they are following, where they can guide through these IoT devices. Okay, and also they are monitoring the health of the defense personnel as well, using this telemedicine thing. The last one is like the fourth one is like unmanned data centers, right? So data centers will have a, so for example, you need not have some person who be there at data center maintain that, right? You can have a drone and a camera and other stuff. So you can just maintain, for example, in the, for example, unmanned petrol bunk is there in the Finland, other companies, countries basically. There you won't find any person because they don't have human resources. That's why they are going for this, adopting this kind of technology, because human resources are pretty costly because there is no human, because hardly they have 1 crore or 2 crore populations, right? So what they will do in a petrol pump, if you go and swipe your card, and then it will how much you enter, for example, 700 euros or 100 euros, you just enter and then swipe the card, and then petrol will come. That's all. So that way, similarly, they are going to use unmanned data centers. So other use cases like, for example, these are all we have seen: dynamic infrastructure, sensing, ranging, wireless intelligence. We will talk a bit about this, okay, later. And you can see that one of the other use cases like non-terrestrial networks basically. So here what they are doing, they are going to integrate the satellites, okay, satellites, because they have a very plenty of satellites launched, right? So some of the bandwidth, right, high throughput satellites are there in the space now, okay. So they want to make use of that speed as well, okay, that throughput as well. Some of the bands are still vacant. Some of the satellites are less less used, very less, it's used very less, below the capacity, okay. That point of time we can use this non-terrestrial networks. So here what is the advantage is that you can have, for example, flights all can be monitored. For example, you can see that ships and any device that you say, it is very easy to cover like some of the application, like a ship. You cannot go and build the towers in the ocean, right? So you can make use of this satellite communication, and then get it integral part of the 5G. So you can experience the higher data rate when you are in the ocean as well. Okay, that's what is the idea here in this one. Okay, and also drones going to come. So drones are going to come. So in order to coordinate the drones as well as this one, so we can make use of these things. Okay, you need not to build any networks there. Now we are going to see, we were talking about high speed, latency, many things, right? Mainly high speed. Whenever we talk of 5G, we used to say, oh yeah, it is, we're going to give a very high speed. So how come it is possible? So throughput is our capacity, is depends upon the many factors. One is bandwidth, right? Operating bandwidth wise, we are seeing that we are going up to 400 megahertz as well, okay? But occupied bandwidth will be somewhere around 200 megahertz, right? So bandwidth is plenty of bandwidth we got now for the 5G. But in 3G, we had 5 megahertz, and LTE, we had 20 megahertz, right? So here we are having plenty of bandwidth in some bands, okay, not in all the bands, all the frequency bands, some bands. For example, in 78, we have 400 megahertz, but it will be allocated to operators like for at least 100 megahertz, okay. For example, in some band like a band 1 or band 40, you will have a band 1, you will have a 60 megahertz like that, okay. So bandwidth is higher. Next is that, so channel matrix. So see, signal processing algorithms are much advanced now. We can make use of that, multipaths to make use of that, and also spatial multiplexing can be done. Next is that SNR. SNR, how come it is? See, you can see that this is a very good relationship. Yes, so when SNR improved, then you can improve the capacity. So that's what we saw in the comparison with the traditional and 5G, that we are going to point the beam to the user, not in the broad coverage, right? Therefore, your SNR is getting increased. Therefore, you are getting the high throughput basically. Next is a number of TX antennas, number of RX antennas. Next is the, sorry, excuse me. Okay, channel matrix. Channel matrix is very important because we are going to process the complex algorithms basically. That's why channel matrix is very important. Okay. Now, next is that frequency of operation. So we'll just slowly touch upon the frequency of operation. Because so far we have seen bandwidth, right? So how they decide the frequency of operation, that is very important because, for example, they will not randomly say, no, yeah, you can go and use 3.5 gigahertz. You can use 600. No, there will be plenty of measurements will be done for this. You can visit New York University, Rappaport, personal page. He has done a lot of measurements for this each band. Okay, for example, you can see you will consider many scenario. For example, concrete wall, wooden brick siding, and then aluminum siding, and metal walls, and office furnishing, all that stuff. So he will pass this 900 megahertz and then observe how much it getting attenuated. Similarly, 2.4 gigahertz, how much it getting attenuated. Based on that only, they will decide that, okay, 2.4 gigahertz can be used for, because it is having relatively low attenuation for the some of the features. So what I can do, I can use for this Wi-Fi networks, okay. But in 900 megahertz, I can use for 2G because of this kind of things, okay. And you can see that some kind of windows we are having. For example, when you analyze the uh, when you are transmitting the frequency, then this is from this paper basically. You might have seen Rappaport, it has several papers on this. So he sweep the frequency, see, he transmit the frequency and sweep the frequency from so many 0 to 400 megahertz, okay, and then identified that how much it is getting attenuated based on the atmosphere, in the atmosphere. Based on that, he has seen some windows. For example, you can see green part. We can make use of that. So we can make use of these bands for our 5G communication. That's what is being you know identify clearly visible from this plot basically. Next is, no, you can see that there are two bands. One is sub 6 gigahertz. It's now currently it's no more sub 6 gigahertz, because 3GPP FCC has defined that sub 6 gigahertz is going to be more than a 7 gigahertz basically. Okay, so because it started with the sub 6, that's why we have started using this word. But now it is going to be more than 7 gigahertz basically. Okay, coverage and mobility will be catered for in the sub 6 gigahertz, because when you go for low frequency, lambda is higher, therefore you can cover the larger distance. When you are going for higher frequency like millimeter waves, as the space attenuation is directly proportional to the frequency. When you have a higher frequency, you will have a higher attenuation. Okay, that's why we cannot use large coverage application for this this band for the large applications. Therefore we can make use of that for small cells, and also for the high capacity. For example, in sub 6, if you talk in terms of 10% of bandwidth, it will be hardly 200 megahertz or 300 megahertz. When you if you talk in millimeter wave, 10% of bandwidth, it will be in gigahertz. Okay, so that kind of capacity we are getting. That's why high capacity, we are going to use this FR millimeter waves, and also for the low coverage. And here we have a large coverage, but capacity will be low. Okay, and some of the antennas, for example, GSM antennas were like this, but now 5G, you can see it's very compact. So the why they are, second reason is why they are going for millimeter wave, because of this. You can see very compact antenna can be made. Okay, and you can see that some of the massive MIMO antenna, base station antenna. This is for the base station antenna. So earlier we had this much big antennas. Now, okay, now radio antennas all put together this much size only. Radio antenna, baseband processing, RF, everything put together this much size only. So you can see what is the comparison. So you can see this much big antenna is being used for the in the 2G, 3G, and other stuff. But you can see that how much it compact it has come in 5G. Okay. Next is frequency bands. Some of the defined frequency bands. Okay, in the 3GPP basically, you can see that FR1 is 410 megahertz to 7125, but it is now revised to more than 7.5 gigahertz basically. Okay, and some of the band is being widely used in the various across the world. Okay, and these are all some of the millimeter wave bands basically, which is being used. And you can see the carrier aggregation bands. So you see 3GPP specification. No, we will talk about this later. So specification will dictate which band to be used in which region. It is very clearly mentioned. Okay, and that's what we have to follow. Next, okay. So far we have seen that frequency bands, frequency of operation, and other stuff, right? Now we will see a system level how the 5G will look like. Okay. So the being it in the UE, or UE means your mobile, or it can be a radio unit. Okay. Will basically have a baseband unit, which is your FPGA or a SoC based system on chip, or a Xilinx system on chip, or ASIC based solution, or anything which will deal with the, for example, coding, modulation scheme, modulation, and other stuff, and beamforming, MIMO processing, all will happen in the baseband. And IFFT, DAC, deframing, framing, and many functions are running. Okay, and in this baseband, then you will have RF. Then it is connected to the antenna. Okay, so here why we are going for beamforming. So because see, you can see that beamforming has a two type of a beamforming. One is user by user beamforming, where user will be sent individual beam to cater for his requirement, his or her requirement. But whereas here you can see that multiple user per cell, you can have quad beam antenna, where you can cover in each beam, you can cover multiple users. This kind of stuff is there. Here algorithm is very less complex, whereas it is very much complex. The channel matrix also will be a much complex. Okay, so this is what done, and this is a high level block diagram of the any device or radio unit, you can see. So this is basically radio unit thing, but we can see that beamforming devices will be there, which we call it as a front hall processing unit, and then you will have a digital radio processing unit will be there, where you will have a lot of functions like this. For example, DUC, digital up converter, down converter, and a DPD, CFR, FFT processing, FFT processing, resource mapping, demapping, beamforming processing. So many functions will be there and are running in one small board. Okay, now that much compactness has come. Okay, very small board handle these many functions. Earlier we had, for each function we had individual equipment. Okay, that's why the old phone you might have seen, right? Single phone we used to call it as, right? That had a very big phone. Now everything, all the function passing in chip now. That's why we are getting a very compact thing. Okay, and you will have RF front end and then antenna arrays. Okay, this is for the for example any 5G system that you talk about. And this is another kind of view of any system model. You will see that baseband part, where you apply all those algorithms, whatever you, for example, signal processing, many PhD scholars are doing, many research is going on, right? Signal processing, image processing, all the processing. Okay, and also you use network NS2 tools, right? So how you coordinate these things, and how the coordinate nodes and other stuff, right? So all passing will be done over here in the baseband. Okay, and you will have a transceivers. Okay, transceivers will, for example, here, see, basically the entire baseband, right? Your signal get processed with the digital domain. Okay, digital domain. Okay, ones and zeros. Okay, here the frequency of operation will be intermediate frequency. It will be 200 megahertz or 400 megahertz. Okay, this will be done. Then it will be converted using digital up converter, basically. So digital up converter, it will convert the intermediate frequency to the RF frequency, basically. Then you will have digital, once the processing is done, entirely done in the digital baseband side. Okay, then what you will do, you will convert that into analog signal. Then you will amplify according to the requirement. So how this done? For example, see, my output power of the radio, for example, let's say 40 watts. Okay, 40 watts. My baseband chip, no, baseband chip will process all the signal, and DAC output I am getting minus 18 dBm, for example, minus 20 dBm or minus 30 dBm or minus 20 dBm, whatever it may be. Okay, so now what I have to do, I have to make the output of radio should be 40 watts, right? 40 watts, we get roughly around 56 dBm. Okay, so I have to get that one, right? I have to, what I have to do, the DAC output, whatever I'm getting, I have to amplify that, right? For which I need to use amplifiers. Okay, amplifiers, and also along with the filters, right? We should not amplify the signal which is unwanted. Okay, we have to filter out or download the signal, then you will amplify that, and then you will give it to this one. Okay, so why we require that? For example, if you go through 3GBP spec, for small cell it is 24 dBm, which is a 250 milliwatt radio, and then for micro cell you will talk about, I think, 34 dBm, and then macro cell it is 46 dBm, I think. Okay, so beyond 46 dBm it will be a macro cell. So why they are defining that? For example, if you want to communicate, uh, basically it boils down to EARP calculation, basically link budget calculation. So for example, if you want to cover 100-meter, what should be the power level of my radio accordingly, so that, because the signal will experience the path loss in the area, right? 1 minute. sorry. Okay. So here, what will happen is, see, for example, a user is here, okay, somewhere over here, for example, 100 meters away. But a user is here. User can receive and process the signal which is having minus 70 dBm, minus 80 dBm. Okay, that is the sensitivity of the user. So I'm having path loss of, for example, roughly around 70 dB. Okay, so 70 dB I have path loss. My user can receive only up to minus 80 minus 70 dBm. Let's say. So 70 dB path loss is there, minus 70 dBm. So I have to accordingly align my power over here so that I can reach that user with at least minus 65 or minus 70, like that. Okay. So accordingly I have to calculate the what should be the output power of my radio. Okay. Then so that it compensated with the path loss and then reach to the user basically. Okay. Next, we will talk about a bit about the massive MIMO. Okay. So massive MIMO, because massive MIMO, see, the thing is, my traditional MIMO system, no, traditional MIMO system will have like, we do not traditional MIMO system will have MIMO features, but some of the MIMOs will not have beamforming features. Okay, so that's why we are going for this massive MIMO. Massive MIMO itself, we have too many things, like for example, fixed beamforming, dynamic beamforming, and attribute based beamforming. Several beamforming techniques are there. Okay, so here also still some of the beamforming being used, and the code bit based beamforming, many beamforming techniques are there. So why we go for this massive MIMO is that, see, in because the inputs are the network strategy. So what is the strategy? Because you want to put one radio to cover, for example, a very dense urban. For example, if I can say in Chennai, some of the place called, for example, Rich Street or somewhere, okay, where you will find a lot of people, right? Lot of in Chennai Central Station. So where you will feel a lot of people are, for example, if they started using downloading and videos at a time, then you cannot cater for them, right? So that's why we have to follow the retro strategy that, okay, I can put one radio because I don't have much space there to put all the towers, right? Poles and other stuff. I can put in that case, I can put one radio, give which can cater for all the users, most of the users, with a better user experience. And the second thing is that when you are going for a football ground, right? Football World Cup is going on. There you will see plenty of audience will be there, right? You have to cater for them. So with a better user experience, that point of time you can use this massive MIMO. So many strategies they have, and also network assets. You are going to instead of having 2-3 radios, you can have one single radio, massive MIMO radio, to cater for the users that is there. And it's mainly need for the coverage, capacity, and the user throughput. These are the three main needs, and ease of deployment. So constraint is that ease of deployment should be there. For example, here, see, in traditional radio system, no, you have to install radio, base station, baseband, base station, then you have to lay the cable, and then you have to install the antenna and the tower, and all that stuff are there. Here, you just simply install this massive MIMO radio. The fiber cable will come down, and then one power cable will come down. That's all. Tap it. That's all. You are done. Okay. That's how ease of deployment can be ensured, and the energy efficiency is there. We have explained. Total cost of ownership also getting reduced because of this massive MIMO radio. This is the basically the need for the massive MIMO. And solution is, for example, there are number of solutions are available in the massive MIMO radio, or ORU, or RRU, or many things are there, and it has array capabilities. Basically, array capabilities, why we use array capabilities? Because it has to point the beam towards particular direction, and you need to do beam forming, right? Next is that this is how the thing is. Like, for example, you can see that, see, you need to have baseband processing unit, and a radio unit, a remote head, and then passive antenna. All three together, you will, these three should be there in conventional solution. You can have only one beam, okay? Whereas here, so you can see that, baseband, massive MIMO radio. Yeah, now all together it's coming as a single box where you can have multiple beams can be generated. Okay. Next is that you can see that what is the advantage of this massive MIMO is that you can see that the simpler advantage is that, see, higher beamforming gain, so that user can get better SNR. Therefore, the better user SNR. Therefore, the throughput increases. And second thing is that we are have when you are finding interference, right, interferer, right, when you are, for example, this user is getting catered by this particular cell, but it is interfering this cell as well. This user interfering this cell, but it has to communicate with the only this cell, but it is interfering with this cell. Therefore, we can send the null towards this user so that we can avoid this user interfering this particular cell basically. Okay, next is that single user MIMO, multi-user MIMO. What is that? Is that you can see that you can have all 3 layers of data. I mean, it's 3 streams of data will be sent to single user, or 3 streams of data can be sent to individual user. Depends upon the channel matrix. So basically, correlation will be taken. So the correlation, if the correlation is less, we can send multiple data streams using multi-layer MIMO, and then to the multiple user. If your correlation is less, okay. Next, massive memory radio unit architecture perspective, system level perspective. You can see that you will have a digital front end, analog front end. Digital front end means what I was telling, right? Digital, digital up converter, down converter, and some of the processing will be that happen in the digital side. And you can see that beamforming chips will be there, and layer one means physical layer basically. Okay, and then this is the radio unit will have all this stuff: baseband chip, layer one processing and beamforming, and radio ASIC, analog front end, all put together. It is there, and then it is communicated in this radio basically. This is actually basically traditional radio, but massive MIMO will have all together in the one box basically. Okay. Now, as we were telling that massive MIMO, the heart of the massive MIMO is the phased array basically, because you have to do the beamforming, right? So here we are having 2 kind of beamformings. One is analog beamforming, where what you are doing is you will have one baseband processing chip that will be split into multiple RF chains, and then connected to you can steer the beam in any direction that you want. Here the problem is, the advantage is that you are using only one baseband chip, and then but disadvantage is that capacity is low. Second thing is that if you want to do change the cater for the other frequencies simultaneously, you cannot do that, right? That flexibility is not there. In order to do that, we are going for digital beamforming, where digital beamforming has baseband digital baseband processing and individual digital baseband processing for each RF chain, where you can play with the many subcarrier spacing. There is one term called subcarrier spacing in 5G or LTE. So you can play with the many subcarrier, one subcarrier spacing for this one. So this is basically mainly helpful in network slicing basically. For example, some application need some kind of a low latency or high latency. Some application need higher bandwidth or something like that. You can play with this and then do it. Okay. So, but the disadvantage is that cost-wise it is quite high, because you are going to use this multiple baseband chips, and the complexity also very high. So, in order to avoid that, in order taking advantage of cost reduction and also compacting in nature, and also the multiple baseband processing, we are going for hybrid processing technique, where you can see that digital processing will be there individually, and some of the RF chain will be split into multiple RF chains, and then connect to this massive memory radio basically. So, but in general, in massive MIMO, they are using digital beamforming. Very rarely they use this kind of technique. Okay, but in traditional, radar system and all, they use this analog beamforming. But now they are migrating to digital beamforming as well. Okay, because here we are having a lot of flexibility with the software only. But we are using phase shifters, which is analog, which need some kind of active circuit to tune to the particular thing. Okay. So any beamforming will happen, for example, based on the excitation, right? Based on the amplitude and phase excitation, you can steer the beam in any direction that you want based on the array theory, basically. Okay. Next, you can see that this is how beam can be steered. You can see how the beam is getting steered in this one. Okay. Now, let me explain. How the you might be asking, okay, how come it is beam can be steered in this fashion? No, there is some kind of implementation to be done. Okay. For example, one easy implementation is that, or readily available implementation, that it can be dynamic one or a fixed one. So, for example, I'm going to say Butler matrix. Okay, 4x4. For example, we'll see Butler matrix. So, how beamforming can be they can be achieved. For example, this is the input I'm having from the baseband chip. Okay, This is the antenna element basically. It Butler matrix has you can see that coupler, directional coupler, and crossovers, and the phase shifter basically. Okay. All put together is there. You know that when you control the amplitude and phase of this antenna element, you can control the beam as well, right? So here there is a fixed conversion. For example, this is connected to here, this is connected over here, this is connected. So all four contributing for this. So combination of phase amplitude and phase can be generated using this Butler matrix approach. So if I excite this, I will get a beam like this. Okay. If I excite this port, I will get a beam like this. If I excited this port, I will get a beam like this. If I excite this port, I will get a beam like this. So that I can control. So how come I am getting this kind of beams when I excite each one of them? Because this is going over here, this is going over here. So from these two only I am getting all the four connections, right? So if I am exiting this part, then it will apply the certain amplitude and phase over here. If I excite this part, it will apply certain amplitude and phase over here. That way we can achieve this kind of thing. Oh, sorry, we got a simulation perspective. You can see that I don't know what will happen, because what is happened. So this is the arrow basically. Okay, so simulation perspective, when you want to simulate this kind of thing, you cannot do alone, right? Okay, because you have to, for example, you can see that in simulation perspective, you can see that this kind of you have to cope up with the baseband and RF chain processing, and because RF chain has power amplifiers and other stuff, so where you need to ensure the matching and with the antenna, right? If you individually design antenna, it will work perfectly fine, but when you integrate with the system, it will be mesh, okay, because matching will be gone, and then you will not get the desired radiation characteristics and so on, right? That's why we need to go for core simulation, right? ADS can be used for advanced design system. Stool can be used for the designing amplifier, and then the CST can be used for the antenna design. Okay, so what you will do, you will design an antenna, and then you will feed the you will design an amplifier over here, and then you will feed the output to here, and then you will model the antenna, and then you will you will measure the radiation and diversity performance, and then which will be fed as an input to this one for the amplifier modification basically. Okay, because some of the time what will happen is matching will be ensured, but radiation characteristics will be poor. So that based on that feedback, it will what it will do, it will characterize the amplifier and then do that, right? So how it can be done? This is how it can be done. Okay, here you can see that input matching network and transistor amplifier output matching network, and then antenna element. Okay, this is how this is the TX line, this is the RX line, basically RX lineup. This is a transmitter lineup, and this is the receiver lineup. Okay, so here what we are doing, so we are going to see we're going to tune these input and output matching network, so that we will get the desired performance of the amplifier as well as the antenna element basically. Okay, so this is how the simulation can be done. So this is particularly from the ADS itself. Okay, we can see that we can design the amplifier circuit, transceiver components, transceiver component from in the ADS, and then in ADS itself we have a antenna design momentum tool, where you can model the patch antennas and other stuff. So what you can do is you can select the certain models, okay, in order to apply all those weights to the you can send the signal to through that, and then you can apply all the amplitude and phase weights to here, and then you can control the beam, and then you can see, okay, you can experience and see, okay, if I apply the particular model, then what beam direction I'm getting. If I apply the particular coefficients, what beam direction. You can see here the phase shift can be you can just create a mini predefined parameter, and then you can sweep it, and then you can see the beam sweeping happening. Okay, that's how we can see. And also at the same time, along with the beam sweeping, you can also see by MATLAB has a physical layer 5G NR toolbox basically. So what you can do is you can generate the signal from the toolbox, and then give us an input to the RF transceiver chain. Okay, then you can that will be fed to the array, and then you will steer the beams, right? So when you based on the beam feedback, okay, that you and then based on the beam characteristics, you can go you can feed this input as a feed these parameters as an input to the MATLAB, and then you can simulate the UE in particular direction, and then you can see that, wow, okay, what is the throughput I'm getting, and what signal level I'm getting. All the stuff can be done. Okay, or you can see that system view. There is one software called system view in the Keysight. From Keysight, they have these features, right? They will have a system modulation models will be there. That models can be applied to this RF chain. Then it will be given to the antennas. You can see here that amplifier, and I know you can see the phase shifters, band pass filters, all those filters, all you can design in one particular sort tool, and then you can validate end to end basically, right from this generated signal, and then it is passing through the RF transceiver lineup, and then it is going to the antenna, and the what is my beam I'm getting, so that entire chain is being can be validated through simulations, right? This is how it will be done. For example, you can see here, when you apply this model, it will steer the beam. You can see here that multiple beams are getting steered in multiple directions. That you can validate through this kind of simulation tools. Okay, this was just an example. Okay, now testing part. Okay, testing part is very important basically. Though you do all the wonders in simulation, but in testing is very important, because that only validate the design as well as the hardware and everything, right? So in general, testing can be done in the you might have seen that far field distance, right? Okay, far field distance. Which is in the far field distance. I don't know why this equation come over here. It's okay. No problem. Okay, and then far field distance. Okay, so this is a traditional far field distance. So why we are doing that? Because you can see that in any antenna will radiate in a spherical in nature. Okay, so when you have an antenna surface like this, okay, you are getting a phase offset here. Okay, the allowable offset is, for example, a phase offset is 22.5 degree. If you apply that, and then simply you can calculate, for example, you R, only if you calculate the R1, and then if you find out, is simplify, the D, aperture size of the antenna, D, and then R, and then you can see that if you apply all this stuff, and then if you simplify the thing, 22 instead of 22.5 degree, I think you can put lambda by 8. Okay, then you apply all these things, then you will get the 2d square by lambda in the equations. Okay, and then this is kind of a simulation of this far field. How, see, you can see here that it is starting with the spherical waves, but at the 2d square lambda distance or beyond that, it is almost getting plane waves, right? So that I can get the receive the signal properly, okay, without noise basically. And it has various regions like radiate to near field region, far field region, and other stuff. It's about the antenna. So this is how the testing will be done. For example, in terms of antenna perspective, beam perspective, you can see that just now the simulation we saw, right? This is how the beam will be tested and then measured, and then this is actually basically a 3D chamber. But we in India, I don't think we have a three-dimensional radiation pattern measurement chamber. But it is there in the US or somewhere else. Okay, so three-dimensional way. So basically, radiation pattern means what? How much power is getting distributed in that particular direction. That is the radiation pattern basically. Okay. And in 5G perspective, you can see that you cannot do just like that, right? You have to do a system level simulation, where you can see that in 5G, you can see that UXM 5G, there is from Keysight there is an UXM. This is basically a node B emulator, or you can base station emulator. Okay. Similarly, RNS has RNS has CMW 500 and SMW 500, like that. RNS Rhodes has many equipments like similar equipments in node B emulators and other stuff. Similarly, Viavi Solutions also has node B emulators and other stuff, and Tektronix, and many companies are working in test solutions basically. Okay, NI National Instruments, many companies are working on that. Okay, so here the fundamental principle is that, see, you are going to emulate the whatever base station will do, right, in the lab environment basically. So what will happen in the field? Okay, whenever in radiation base station is radiating in some signal and is getting received by the UE, what will happen in between? So all the stuff can be modeled as a software, right? Software stack, and then we model as this particular hardware, right? So here this is kind of emulator. Okay, then you will have a channel emulator as well, because we have to consider a building scenario, and tree scenario and rain scenario and other stuff, right? So these scenarios are already been developed by some of the researchers. For example, Fraunhofer Institute has some kind of channel models for then relay fading model, and these in channel emulator will have those models only. For example, New York University has some model, Stanford University has some model channel models. So all those models will be implemented in the has been implemented in this channel emulator in order to emulate the particular scenario, right? And the fading scenario. Then you will test the UE. So that why we are testing this, in order to see that this UE will perform as such, whatever it meant for, right? So that is so kind of real time simulation is testing is in the emulator mode. It is being done. Then so once it passes from here, then it will go for a trials basically. Trials basically. Okay, go for a trial, and then there also they will test it. After that, only mobile will come out. Once it is certified by all the bodies, required bodies, GCF and FCC, many bodies will have to certify the mobile that okay, yes, it got tested in this environment, and then it is very good work, performing well. Then only the device will be allowed for the means marketing basically. Okay. And if you want to test beamforming, the beamforming will be like this. Okay. And if you want to test, you need to have a 2D positioner where you can rotate it horizontally, as well as the vertical. Okay. So this is how they will be done. Like for example, here you have a device which is steering the beam in this particular direction, any direction that you want. Here we have horn antennas. Okay. Dual polarized horn antennas will have. So, for example, if a beam is coming over here, I already know what is the position of a horn antenna. Based on that, I can find out, okay, yes, the beam is in the particular direction. For example, let's say 15 plus 15 degree. I can able to identify in all which direction the beam is coming out. Okay. Next is that simulation tools. Some of the simulation tools, for example, MATLAB, ADS, HFSS, and SPICO and AMPRO. Many tools are available. And testing solutions, you can see that at Keysight and Andritsu. Yeah, it's one of the big company basically from Japan. Nowadays, was from German, and YAB Solutions from US, I think. So JDSU, basically JDSU was there, then they converted to YAB Solutions. I think these also have a good presence in Japan. So these are some of the companies they are working on the simulation side as well as the testing solution side. Okay. Now we'll move on to standards perspective. Okay. So I think I have some 20 minutes time, so I will try to cover this one. Okay, standards perspective. So when you touch upon, there are plenty of standards are available. Okay, so standards means what? Standards means, for example, you can see that government has a full pass GO, right? Similarly, standards also will have a, for example, standard means, for example, railway track. For example, if you look at the any mobile phone, this should be designed in this fashion only. It has to emit this much power only. Okay, and this should have these many components, right? So standard will be like a dictating body, a kind of dictating body, also a guiding body. So guiding dictating body means it will tell you that this mobile should radiate this much, it should consume this much power only, this many volt only, and all that stuff. You can limit that, dictate the terms. The other things are guiding factor as well. Standard will be a guiding factor that if you want, if you are a new startup company guy, you want to develop some mobiles, okay, based on your software, you want to do some enhancement to the mobile, you can go and refer the standards document, will give you each and in and out details. Okay, how it has to be done, how it has to be connected, how it has to be done, what software to be done, how the protocol to be implemented, what is the, so everything will be there in the standard documents. So each document, per se, it will be 500 page, 1000 pages document, maybe more than 1000 documents are there. If you thorough with that, for example, then you will be, you will be paid like anything, like maybe like, more than salary of CEO. But nobody cannot be like that. Okay, that's what I'm saying. So standard documents will have each and everything in that. Okay. For example, how you have to connect, how you have to case the body, how you have to implement the algorithm, what is the description of algorithm, what is the equation you have to apply for the algorithm. Everything will be there in the standard document. So standards means, it is not something somebody who is creating standard. It is us, for example, as industry guys, who from the industry folks from many different companies will come together and discuss and finalize the standard basically. Okay, create a document and then do it. Okay, because I am basically contributing for ORAN basically, and I have contributed for through my mentor I have contributed for 3GBP as well. So whatever we will do is we will go through the document. If there is any gap, we'll also try to fill. So this is how the contributions made from all across the world, across the industry folks, and then they created as a it is coming in a good shape as a standard document basically. Okay. Now 3GPP has, for example, in every releases they will have a releases like now we are into 3G release 18 basically. So each release they will dictate what parameters I am going to consider. For example, I think system architecture priorities. Yeah, see, they will have several working groups basically. So technical steering groups. Okay, so standard group will have a, see, 3GPP will has plenty of groups. If you go through their website, you will see so many groups will be there. Task group basically. So each group will have their own priorities. Okay, this group, this particular release 18, what I am going to do. Okay, so if each release should have a significant, for example, each G 1G, 2G, 3G, 4G, right? So all are come from here only. Okay, in 1G, what is to be there? What all features to be there? In 2G, what all two features to be there? Because if there is no shift, why we call it as 5G, right? So it can be named as LTE only, right? So why we are calling it as 5G? Because there is a paradigm shift in the features perspective, architecture perspective, and many other perspective. That's why. So each group will have a several working group, right? Everybody cannot be expert in all the areas, right? So that's why each working group will have. For example, I am contributing for some hardware architecture, right? So similarly, yeah, somebody can be good in protocol, somebody can be good in core networks, somebody can be good in interfaces. So each group will focus on particular domain only. For the system architecture means overall RAN system architecture they will focus, and the what all items to be covered in this particular topic. For example, see, this is how this is come is, for example, if I am from Starlight, so we are doing some R&D internally, and we are seeing that okay, yes, this has some potential. We are developing some feature. This has some potential. We'll try to push it to standard to mandate for the other vendors to follow. Okay. Similarly, Qualcomm will do some research, come up with some, for example, AI ML algorithm which can optimize the beams and all that stuff. So they will add as that as a work item. Okay, but that has to be mutually agreed by all the members of the particular working group, and then, so that it will become a standard basically. Okay. Similarly, RAN will have several features. For example, MIMO, this should be this much, downlink, uplink, artificial intelligence, and all that stuff. So how what are all features to be enhanced, what are all features to be added in each release? No, they will discuss. Then they will make it as a release, and then we can make a contribution on top of it. Okay, this is how the 3GPP works. Okay. Any standard will work. Okay, so you can see here that, for example, release 18 in attractive mode. I think Rhodes was, they presented in this fashion very nicely. That we can see these are all the work items. There we call it as work items, change request. Okay, work item means I'm proposing something to the forum that you can consider this. Okay, because it has a potential changes. You have to modify this document according to this, or it can be a new feature as well. That is called as work items. And change request means based on the document that if you find some gap, you can fill the gap in terms of editorial corrections, in terms of feature addition, in terms of feature corrections, anything you can do. Okay, so here you can see that this is what for example you can see P2X in cellular vehicle to everything in FR2 bands they are targeting in this release 18. And you can see that non-terrestrial networks they are focusing. Okay, they are going to focus, and ultra low latency CSA reporting. So many things you can see for flexible duplex technology, because some companies mainly investing heavily on this particular technology, right? They are very good in baseband. Then they will work on this and then find out, okay, yes, this can be a good feature. This is how hardware will be developed, right? The standard each work item will be added. So here you can see a 5% 5 megahertz UV bandwidth power saving enhancement, backup signal. This is one kind of work item they are proposing, and then this will be worked out and then mutually agreed by all the people, and then it will be mandated as a standard parameter basically. Okay. And you can see that evolution and in sensing and ranging. So that is a very good word actually. Sensing and ranging. That is what happening in evolution, all the evolutions, right? Because sensing the requirement, and we need high coverage requirement, and also sensing the user, and then cater for each user. That is the prime motive basically. In release 18, you can see that sidling automotive, you can see that drones and industry. This is automation for the, for example, Amazon. You might have seen the video, right? Amazon automation. So it will you need not have any person to go and pick the right material. There will be a warehouse. Each component will be scanned through QR code. This will device will scan the QR code and then pick the appropriate whatever product you are ordering, right? Now it has become AWS based services, Amazon web services basically. So all has intelligence. If you order, the order will directly go to the, for example, I don't think they might have implemented in India, but in US they have implemented that. When you order in the Amazon website, you go to straight away the request go to this controller of this drones basically, or we can say bots or anything, right? Then it will trigger the particular drone, go and pick the material, and then give deliver to the particular gauge. Okay, then that now they are going to deliver through drones as well. So it will deliver to the particular drone will pick that package, and then it will deliver to the particular location. So all will be address will be fed, and the map route will be fed. All will be done in this fashion. Okay, so that's why sensing and ranging. Okay, so the coverage range, and then also so sensing ranging, why they are maintain is because they are mainly focusing on side link. This is used for cellular vehicle to everything. If you go on search for side link, you will get a lot of information. Sensing the cars, and then ranging, and how much coverage range it can provide, and then that is what is discussed over here. Okay, and if you see in terms of advancement of 5G, you can see that in release 18, LTE release 18, each releases will have some work item. UE specific only, like that, 4 layer per UE, like that it was there. In release 15, LTE Pro, they have improved a lot of features in the LTE itself. Okay, multi-layer MIMO and other stuff. Okay, but in 5G, you can see coverage and the spectral efficiency requirement enhancement have been done when you compare with the LTE, and beam measurement reporting, indication, beam failure recovery, all that stuff have come in this particular thing. Okay, so but here it is user specific only. Here you see there is no beam management is done over here. Failure recovery, nothing is done over here. But here it has intelligent to do all these things. And you can see that 8 layer per user, 12 layer multi-user MIMO, all that stuff is being used over here. Okay. Now, okay, 3GPP. This is one perspective. ORAN, okay, Open RAN. So Open RAN means, see, let me give you a glimpse of it. Okay, Open RAN. You might have heard this buzzword in many articles, right? Okay, so why they went for Open RAN is like, for example, in traditional vendors, right? System like RRH will be there, which will be remote radio head will be in tower. You will have baseband unit. Okay, baseband unit. Okay, both will be the proprietary hardware. Proprietary means become one vendor. For example, Nokia means Nokia will have both, and Ericsson means Ericsson will have both. So what is happening is, so when you want to enhance the features, when you want to enhance the RAN networks, then what is the major blockage is that. So for example, it is up to the Nokia to develop this. For example, Nokia will spend some money on the R&D, and then they will develop advance this feature. For example, they want to advance this baseband algorithm and other stuff. It will take much time. There is no competition for them, right? That's why they are the main pillars. For example, Nokia, Ericsson, and Huawei. You might have seen so many companies are wiped out. For example, Motorola wiped out, Lucent wiped out, Alcatel Lucent also wiped out. Now, so it's because it's become a monopoly, right? So you are when you it's up to the operator also facing a lot of issues. For example, if you this BBU gone, then they will pay heavily for this replacing the BBU. Operators are facing a lot of issues. That's why they wanted to have a split in it. Okay, for example, some part of the work will be done by some vendor, some part of the work will be done by some other vendor, right? Some of the processing. Here you can see that kind of split only happen, right? For example, you can see that RE will be from one vendor. Okay, here you can see that this will be a DO will be a distributed unit, RE will be radio unit, CU will be control unit. Okay, centralized unit basically. Okay, so they are splitting. See, RRH and layer 3, layer 1, layer 2, 3 means physical layer, data link layer, and network layer. I think. Okay, layer 1, layer 2, layer 3. Okay, so here the most of the processing is done in OSI layer. No, you will see application layer, presentation layer, all the stuff, right? So application layer is your browser or whatever device you are using, and then it is sending the data. It will be presented in a good format, and then it will come to transport layer, then network layer, then it will come to data link layer, where it will convert as a packets, and then it will be sent to the physical layer, and then it will be sent to the RF front end to RF, either RF or optical to the to reach the destination. The data will be delivered to the destination. Okay, so here what they have done is they are most of the baseband processing are done up to L3 level, okay, layer 3 level. So what they have done is, see, they have split, so they have splitted this this processing, layer 3 processing in the centralized unit, and the layer 1 layer 2 processing in DU. Okay, this was one split. But in ORAN, what they have done is, like, they have done this interface is not a proprietary interface basically. So therefore, what will happen is, some company can make, for example, like STL is making ORUs. Okay, some company like a DU, ODU, for example, Dell Technologies and Radisys and Mavenir and Altiostar. Many companies are making ODUs. Okay, and some company will make CU. Okay, so what is happening is, here there is no dependency in deployment, so you can have a rapid deployment. You don't have to depend on one vendor in deploying anything. Okay, what they are doing, so they can go with, for example, if this guy is not delivering properly, then they can go with the other DU vendor. If this guy is not properly delivering, they will go to the other RU vendor. So they can, what they are doing is, so all will be compliant. These interfaces are standardized interface, so it is not open interface basically. So therefore, this radio unit will comply with this front hall interface. This audio will be comply with the both front hall as well as the F1 interface. Therefore, you can integrate, we can say interoperability will be ensured, so that it will be made available for the customer, right? So it will see what is driving is, driving factor of ORAN is, R&D, more research focus, more feature enhancement at less cost. Total cost of ownership will be reduced, and you will don't have to rely upon one vendor. If that vendor is closing the company, then you have to spend heavily to replace that equipment. Here there is no that game is over now. Okay, so you can go with many vendors and then operate with each other. So but the problem is, this vendor may blame this vendor for some reason, right? That coordination to be done, that's all. So otherwise, operator, as an operator, it will be advantage for them, because new features will come up in each, because they are investing heavily on this. So they will try to add new features, right? That way, operator is getting benefited. Okay. This is the open RAN in short terms. Okay. Now, RAN architecture perspective, you can see that, you can, in open RAN perspective, we'll have orchestration and automation. We'll have SMO kind of architecture. It's a kind of management will be done in this level. Then you will have a RAN intelligent controller. This is a RAN architecture perspective. RAN intelligent controller. Here, what they are doing is, see, depend upon the number of users, depend upon the applications, it will adapt intelligent controller. Okay, see, it can identify the issues, and then it can detect the issues, and many management can be done in the intelligent manner as well. Okay, not in the physical mode. Okay, earlier traditional networks. And you can see that, so ODU is there, OCU is there, CU is there, RU is there. This is how, see, it is getting managed. Okay, here mobility management is done, QoS management is done, intelligent controller. Here the problem is, some kind of intelligence is given to the network to manage this. Okay, so with the help of trained models basically. Okay, so what will happen is, see, you run intelligent controller, what will is, to learn from the past experience, and it will act upon it. Okay, that's how now there's some kind of intelligence going to the network as well. So this is how, in simpler fashion, you can see this kind of architecture will have. EPC means this is a packet core, next generation core, basically core network. Basically, it is connected through interfaces to the CU, DU, and the ORU. Okay, so this is the high level block diagram of the new ORU. Basically, ORU, as we mentioned, will have a baseband. This is the baseband. Okay, and then you will have a FPGAs and other stuff. These are all the baseband processing is done. Then you will have a digital front end. You will have a DDC, DPD, and other stuff. Then you have a RF front end. You can see that the DAC and LNAs, power amplifier, and other stuff. Okay, duplexer and circulator. Okay, so other stuff are there. Okay, this is the high level block diagram of this radio unit. Other standard alliances are, for example, OpenRF. Okay. Now you can see that many mobile vendors are come. Okay. Earlier, no, hardly you will find Nokia, Samsung, some Ericsson, and Sony Ericsson was there. Only three, four vendors. Now you can see plenty of mobile vendors. How come it is possible? There is a fundamental shift in the standardization, right? So how are they? Now you can see most of the mobile will look like same thing. You will not hardly find very, you can see find the difference only with the software perspective and the GUI perspective, and some kind of features like camera, or some kind of some. So only few enhancement will be there in the between the mobiles. Okay, and apart from the processor and other stuff, you can say if you compare the Samsung and Nokia phone, you just place it over there, same configuration phone, you will see size will be same, exactly same. Only small changes in the cosmetics will be there, and also in the software will be there, right? How come it is possible? Because of the some of the forums like this, OpenRF, RF, MIPI Alliance, and many alliances are working on that. So what they have done is, it's like Open RAN. They have done, very fantastic job. Like, for example, software. See, they OpenRF have what they have done is, they have created a forum where they have three working groups, which will work on, for example, software perspective. They will define the standard. This is how your software should be. This is how your hardware should be. This is how your interface should be. This is how your architecture should be. This is where you have to place your antenna. This is where you have to place your processor. Everything is defined, clear cut defined. So that, what they are doing, they are taking that reference design. Most of the mobile vendors are launching the mobile in a very fast manner because of that only. Reference designs are already available. You will contact the component vendors and assemble it and then sell it. Okay, you will dump the software and sell it. That's how it happens. Okay. Here you can see software interoperability. So interoperability is, here you can see that RF power, between the RF power to RFIC, this is how it should be communicating. All are well defined now in this standard basically. Okay. So each transceiver sign, what should they have, all that stuff is defined in this particular one. So hardware abstraction layer basically, it is standardized basically. Okay. So therefore what is happening? So you know what you want to do, right? So you have a high level reference design already available. You have to play with that, and then you start launching the mobiles. Second is that hardware interoperability. Hardware interoperability means, see, this is a particular RF front end chip you have, RF blended board you have. Okay, so what will happen is, so it will interoperable with this RFIC and other things, right? And it will interoperable with the power as well. Okay, so they all will be designed in compliant with this particular OpenRF basically. In compliant with all component individually will be designed in compliant with this OpenRF thing. So what they will do, if it is individually compliant, and then with along with the interfaces and other stuff, what you can do, you can simply buy this from one vendor, this from one vendor, this from one vendor, assemble it. That's what is going on now. You can see that Micromax or many mobiles, Chinese mobiles, Chinese and Amazon launched so many mobiles, right? What they are doing, they simply, whichever is suits for them, and they do some software modification. They buy this from someone, buy this from someone. That's all they have assembled. And the other alliance is MIPI alliance. Here it see between interface, right? For example, you can see sensor, near field card, GNSS, application processor, and cellular modem, RFIC, Bluetooth, and everything is there, right? The interfaces between all the touch screen, displays, cameras, audio codec, and other stuff, microphones, and everything. So in the interfaces between all of them are now standardized now. Okay. Therefore, each individual component will be compliant to this interface. Therefore, you can simply buy that and then assemble it. That's all. So because interface is all are defined in well versed manner. Okay. So we got all interfaces between displays and everything interface is. That's why you can if you buy one phone, they are not going to buy make accessories for all the different phones in different manner. Okay. Now you can see that most of the phones will have similar interfaces, similar cards. So that that interface cards will fit for all the mobiles across the design. For example, if that particular mobile manufacturer follows the same reference design, then you can use that spare. Spare is more readily available for all the vendors, right? That way we are getting most advantages, and also spare will be cheaper cost as well. Okay. And the future of 5G is like, as I mentioned, I think take time up. Okay, I will just take 2 minutes to cover this. Okay, so now you can see that they are going to run most of the functions in the in stack software stack itself. Okay, because it is going to be open stack and several works are going on. For example, in most of the RF, even RF functions as well, it's going to be in running as a software as well. Okay, it's going to be run in software in stack basically. Now world is moving. VMware is heavily investing on the Red Hat, Cisco, Dell. Everyone is investing in this particular. Where they will just install one PC server and then they will dump some software. That software will do all the job that hardware is doing. Okay, that's how now they are moving. Okay, virtualization platform and other stuff. And in 5G, that is what is the advantage. Focus on 6G, 5G transition from 5G to 6G. That is the focus now. So many things we are going to have in a software side, and intelligence is going to come. AI/ML framework is going to be there and other stuff. Okay, testing. And 6G, you can see that AI/ML based inspire reduce design, it's going to come because see, you can see that machine learning is going to be applied in all the parts and parts of the device architecture basically. You can see that channel modeling, demodeling, demapping, all the places they are going to apply this machine learning, artificial intelligence based algorithms. And also now in 6G they are targeting to apply these algorithms in antenna system as well, in order to have intelligence, much intelligence in the antenna side itself, so that it need not send the request to here and come back here. So it will have intelligence over here itself. It's going no more going to be a passive device. It's going to be a very active device, which is with some algorithm is running. That's how it's going to be. Okay. So okay, thank you so much. And this is what we have seen. 5G. We have seen some of the 5G key enablers and features and other stuff and applications. And system level, how it is done, MIMO system level, and as well as the mMIMO system level, and how simulation testing is done in terms of antenna perspective and also system perspective. Okay, and various 5G standards and various the learnings from standards, and also how the standard is arrived and what all contributions are made in the each standard perspective, and also feature of 5G and moving forward for the 6G that we have seen. Okay. So thank you all for listening to me. So thank you so much for listening to me, and I hope I was audible throughout the lecture. If you have any questions, feel free to ask me.
Thank you, sir. It's time for query. I request the participants to ask anything need to clarify.
Good morning, sir.
Thank you, madam. Yes, madam. Good morning, madam.
Yes,
Good morning.
sir.
Yeah.
Sir, in any of the part of this communication system, if we want to start our research work in case, so we need to visit some industry or some real-time problem we need to find. So in that case, where we can go and where we can get the issues present in the issues to find out the research gaps, sir, in the industry side or a real-time things.
So one best thing is that you can visit 5G testbed basically. Okay, in IIT Madras. Okay, IIT Madras there is a 5G testbed as well. Okay, there you can see end-to-end system basically, end-to-end tested as well. You might have heard news last month that end-to-end 5G call, first 5G call made in that testbed. Okay, that is one thing. But you may not have access directly, but you can go through Radha Krishna Kanti, Dr. Professor Radha Krishna Kanti. You can communicate with them, and then you can introduce yourself, and then you can get in touch with them. If they have any problem, then you can solve it. The other thing is that when you go through these standards and some of the forums, like so you can register with some of the forums there. They keep on posting the problems as well as the so that way you can get to know that. Yeah.
Okay.
Yes.
Okay, sir. Thank you.
Thank you. So any other questions?
I think there is a query from chat box.
Oh.
What is the difference between bandwidth efficient and spectral efficiency?
Oh, bandwidth efficient and spectral efficiency. It's almost the same. So spectral efficiency can be done. For example, see, let me share my screen. I can tell in RF terms as well. See, for example, is my screen visible?
Yes, sir.
Okay, madam. So this is the bandwidth, right? This is the bandwidth. For example, let's say 10 megahertz. Okay. So I have got the spectrum of 10 megahertz from the regulatory body. Okay. Now, how I am going to make use of this entire 10 megahertz? It's not possible because we have to give some kind of guard band, 9 megahertz, almost 9 megahertz. Okay. But they will even operate only 8 megahertz most of the time. Okay. So if you want to make this bandwidth efficient, for example, if you talk in terms of engineering language, that what I can do, I can design a component that can work the entire bandwidth efficiently. It will not, it should not leakage any power to the adjacent band. That way we can make it as a bandwidth efficient. Okay. The spectral efficiency, it's also I know it should be a bandwidth efficient. So how it is different is, for example, not different, it's an integral part of that. Spectral efficiency means, see, 10 megahertz, I can send, for example, we call it as PRBs or, PRBs like that, we call it as PRBs. Let's say 50 PRBs can be allocated in this 10 megahertz. Okay. So each PRB will have a carriers frequencies. Each carrier will have a slots. Each carrier will have, sorry, if you talk in terms of time domain, 1 millisecond frame will be there. Each frame will have a slots, half millisecond. Each slot will have 14 symbols basically. Okay. So 14 symbols. Okay. So I am having, 14 symbols, which will be, which is the, some of the fundamental chunk, we can say, chunk data. Okay. So now in 14 symbols, I can send 2 bits, I can send 10 bits, I can send 6 bits, depends upon the modulation schemes. Okay. So modulation scheme, how it is helping? For example, if I am using QPSK, I can map the symbols. Each symbol will have 2 bits in data. Okay. If I am using 32 QAM or 64 QAM, 64 means I can code 6 bits for the each symbol. So how much I am getting? 3 times I am enhancement in the throughput. So here what I am using? I am using same 10 megahertz only bandwidth. But what enhancement I am doing? 3 times enhancement I am doing in terms of data throughput, right? So that way the spectral efficiency can be done. This is one way. The other way is, like, if you improve the SNR by the help of MIMO, massive MIMO, then what you are doing with the help of 10 megahertz, only you are catering for multiple users, right? In 10 megahertz itself, we can create, separate into, for example, 3 carriers. You can do carrier aggregation as well. Instead of allocating 10 megahertz to one user, what I will do, 2 megahertz, 5 megahertz, not like this, and just for example, I'm saying 2 megahertz, 5 megahertz, 3 megahertz to each user. That way you can aggregate the carrier. Okay, so this will be catering for some user, this will be catering for some user. This way we can achieve the spectral efficiency basically. Still I'm allocated with this same thing only. And also spectral efficiencies, for example, cell based approach, which was used in 2G itself. And what we will do, they will have a cell like this hexagon shape. So one carrier they will be used over here. After 2-3 cells, they will use same carrier over there as well. This is also a spectral efficiency. There are many examples are there. Yeah. I hope the answer is clear.
Thank you, sir. I think we have got the answer, response from the participant who asked the question. Thank you very much, sir.
Yeah.
Saranya madam, please continue. Participants,
Any
do you
more
have any other queries?
Okay, ma'am.
So thank you all for listening to us.
Thank you, sir, for giving us an insight about 5G overview and its standards, features, and the enabler for 5G, advancement of ORA, and finally demonstrating how antenna simulation and testing techniques works. Simply, you have shown us how 5G technologies works in the real time, and thank you for highlighting and reminding us the importance of a 5G communication in our day-to-day life. As a token of love and remembrance, I take a great privilege to present the memento with certificate for Dr. V. Lingusamy, Senior Technical Lead, Sterlite Technologies Limited, Gurugram. Thank you so much, sir, for your presence and adding fragrance to this 5-day faculty development program, sir.
Thank you.
Thank you, sir.
Yeah.
So, Dear participants, the link for feedback is shared in the chat box. Kindly fill the link. Submit your response in the link.
Thank you all. Thank you,
Sir,
madam.
sir, Lingusamy sir, thank you so much, sir. It was a wonderful
Thank you.
presentation.
நான்
And
எல்லாரும்
everybody learned a lot through your presentation. Thank you so much for
இங்க
accepting
வந்த
our invitation,
எல்லாருக்கும்
sir.
நான் கிரீன்ல
Thank you.
சைன் போட்டு லேட்டுன்னு போட்டுட்டு
Thank you,
Excuse
sir.
me,
அவசர
Mr.
அவசரமா
Pioneer.
அனுப்பிச்சு விட்டுட்டேன். அந்த ஒரு பையனுக்கு மட்டும் நான்
Thank
பண்ண
you so much,
மாட்டேன்னு
sir.
சொல்லிட்டேன். மத்தபடி எல்லாரையும் அட்ரஸ் பண்ணிட்டேனே. சும்மா நின்னுருக்கலாம், எனக்கு எப்படி தெரியும்?
Sir, thank you.
Okay, madam. Okay, madam. Thank you.
Okay. Sanya madam, you can close the session. Please announce the next session will start by 12:30.